Understanding the three-dimensional space that components occupy during PCB design is very crucial, especially when dealing with weirdly shaped components. But often this aspect is overlooked, and multiple revisions of the PCBs are done. To avoid this issue, in this video we are building a project that will help in understanding the spatial requirement of a PCB, along with learning how to keep the project compact and use most commonly available modules on the market. Finally, to add a layer of complexity, we'll try to build the entire PCB using only through-hole components. I really hope this exercise will help in understanding how 3D space on a PCB can be utilized to strategically place components. This video is sponsored by NextPCB. More on them later. I wanted to build a super compact MP3 player with existing and low-cost modules that can be replicated anywhere, either breadboard, perf board, or on a PCB. I built one in the past using a perf board instead of a PCB, and it turned out pretty well, although it had some complications. Building an audio device using perf board and wires can lead to a lot of issues, but particularly with audio noise. If you're interested in seeing how the perf board one is built, I'll drop a link in the description where you can get the full instructions. It's been a while since I worked on this project, so I'll quickly assemble a similar setup to test if it still works. The circuit is straightforward. It includes an OLED display to output information, DF player which can play music from the SD card, and an Arduino Pro Mini to control the display and the audio from the DF player, buttons for the input, and finally a BMS circuit and a LiPo battery for powering the entire circuit. Also, compared to my previous circuits, I have made few upgrades by changing the TP4056 to a charge plus boost converter with a USB-C support and a larger 500 mAh LiPo battery instead of a 300 mAh LiPo battery. This new setup works really well. I've also made some software tweaks to make it more efficient and feature-rich. It now uses less flash memory and offers options for custom button clicks, which we'll discuss more in detail in a different video. Now that we have the perf board prototype ready, let's think about how we can turn this into a functional PCB. As usual, we start with the schematic. We should be able to find some of the components within KiCAD like the buttons, audio jacks, and the connectors. However, KiCAD doesn't have many modules by default like the DF player and the boost converter. So either we have to download it from a third-party website like Octopart and SnapEDA or build one on our own. In this case, I'll build custom ones using the symbol editor. And if you're not sure how to do that, we have a dedicated video on how to build a custom symbols in KiCAD's symbol editor. Here I'm trying to follow the KLC convention while building the symbol, like keeping the ground at bottom, VCC at top, and grouping pins according to the function. Once I was happy with one symbol, I repeated the same process for all the components. With all the components ready, we can return to the circuit and build the schematic. While doing so, let's try to answer one of the questions from PCB Cupid about the difference between global labels and the net labels. So basically, net labels and global labels are used to name nets or connections. But when using just the net labels, the connection names are just retained on the same sheet, while global labels are used for global connection across different sheets. Since net label doesn't have any graphic on it, you can also use global labels to make the schematic more readable. So even though this existing schematic is small and everything fits on one page, I'll use global net labels, as we have already used net labels as an example in one of our previous videos. After making the connection on the schematic, we can start thinking about the components' footprints. Similar to the symbols, to find the footprints for each of the module within KiCAD can be very challenging, as these modules can be made by various manufacturers with varying layout and dimensions. Therefore, we need to be creative in finding or creating a custom footprint. A good example for this circuit would be Arduino Pro Mini, where some versions of Arduino Pro Mini have additional pins on this row, while others have them next to the A4 and A5 pins. In this case, there are multiple approaches we can take. First, we can select one of the Arduinos that can be easily procured and create a footprint for it. Second, we can avoid using the additional pin. Third, we can include both the pins on the footprint. But for our purpose, to keep things simple, I'll go with the second option and avoid using the additional pins. So my design will be compatible with both the Arduino boards. Next, consider the clearance. Modules like this often have significant size variation because of various manufacturing processes with various tolerances. So it's wise to allow slightly more clearance. Unlike me, where I messed it up a bit by creating the footprint with exact dimensions, which caused some trouble while placing the modules, but it was still usable. Next, always double check the measurement of the actual components and try to be as close as possible while allowing for clearance, especially around edges, holes, and sometimes cutouts. Anyway, once we have all the footprints ready, let's assign them to the symbol and open the footprint editor. Start by placing the components and figuring out the layout. Since I've already made something similar to this on a perf board, I'll go for a similar layout design. If you like to experiment more, you can also print out the footprint on a paper and try to understand the placement. The placement of the display and the charging circuit can be tricky. To get a better idea, let's assign all the footprints to their respective 3D models. But again, finding the right 3D model for the footprints can be challenging. So as always, I'll first dive into GrabCAD and try to find an existing model that is very close to the modules I have. In some cases, if I can't find them, we can build them from scratch either by using softwares like Blender or by using professional CAD softwares like Fusion 360 or Onshape. Once we have the 3D model, it's easier to understand the placement of the module on the PCB. It also helps us understand PCBs in 3D and solves many problems like clearance between the modules and spacing between the components. Now with this module in place, we can think about how to design a case around this PCB. Consider aspects like USB port placement, SD card insertion, button access, etc. Also think about mounting holes and how we can place the PCB onto a 3D printed case. Initially for the battery, I wanted to use this 500 mAh LiPo battery, but then I found a smaller version that fits perfectly under the display. I could have found a model and used it on the PCB, but that's too much work. So I've ignored it, but you're completely free to do so. Once everything in place and it looks similar to what I had in mind, I'll start with routing the PCB. Just remember the basic guidelines while routing a PCB, like the track width for signal and power, guidelines about spacing between tracks, pads and wires. You can apply the same guidelines for most of the routing process except for routing the audio signal. Here are some specific guidelines for routing audio signals. Have separate ground connection for audio signals and don't mix them with the digital signal grounds. Avoid sharp corners and twist routing. Keep everything curved. Avoid other signal close to audio signals to prevent crosstalk. Have impedance control for tracks. Use shielding and ground to avoid noise injection and interference. Since this video isn't meant to be an audio or analog design tutorial, we won't be able to follow most of these guidelines, but I highly recommend you do so. While routing, I was forced to route a few connections between the pins. However, I wouldn't recommend doing this as it can cause clearance issues with some manufacturers. So try to avoid this as much as possible. Once the routing and the copper pour are done, I'll quickly generate a Gerber file to send for manufacturing. The next step is something we haven't discussed in the previous videos, the DFM check or design for manufacturing check. This process can be done by us, or usually by the fabrication plant. If they find any design mistakes or designs that they can't fabricate, they'll inform us. We then either let them fix it or we have to rework and resend the file for manufacturing. This adds up a lot of friction and time for manufacturing process. That's why we need to do a DFM check before sending it for manufacturing. We'll be using the online DFM checker from our sponsor NextPCB. They have an excellent online Gerber viewer and a complete DFM checker, which provides a very good information about your PCB and their capability to manufacture it. The DFM checker checks for signal integrity, open and short circuits, spacing between the drills, board edges, SMD pads, and solder mask openings. And if you scroll down a bit, they also show more PCB related specs and parameters used to design our PCB. The other best part about the DFM checker is that it provides an online report with so much information about the PCB. Specifically, they provide the location of the mistakes within the PCB along with the issue and the level of warning that we are facing. Once we are happy with the DFM check and have made the necessary changes, we can send this file for manufacturing. I placed the order within NextPCB website and I received the PCB in around 10 days. But you'll have to wait until the next video to see the manufactured PCB, how we are going to assemble the MP3 player, and finally how it works. If you have enjoyed this video so far, make sure you're subscribed to this channel and don't forget to smash the like button if you found this video helpful. Finally, if you have any questions or doubts, don't hesitate to drop them in PCB Cupid Q&A section. Until our next video, keep learning and keep creating.